All right, so let's get started. And today's lecture is a little bit different from what we've been doing until now. So it's an introduction to large-scale machine learning in AI and experimentation in general. And the reason being, like why I introduced this topic, and obviously we won't go into a lot of detail, but I'll just like introduce you to a few tools that are out there. And a reason being that we've been working with these like really nice data sets that have labels and that have a certain form of a structure. And even if you go online and look for these like publicly available data sets, they are in a pretty good shape as such. So what we have to do is just like pick them up and build our models on that. But now in a real world environment, that's not something that happens. And you know that like for any platform, be it Amazon, be it Netflix, or be it like any other online platform, we as customers are generating data, right? But that data is not in the form in which we need to like implement a machine learning model. So basically the data goes through this like whole process of like how it's created and to the point where we can pick that up and build our models on that, right? So we don't get this nice labeled data set the moment like a customer logs into Netflix, and we can just like pick that up and build our models on that. So a little bit of an idea of how this process works. Maybe like if you in the future go and work as a data scientist or like as a machine learning expert, you will get that nice data because like whatever industry experience I have, usually we are given that data, but it helps to understand how it came about in the current form that's there, and then utilizing that. So that's the first part, like what and obviously like when we build our model, the other important point is scalability. And scalability is important because we need to understand that the data is coming and it's like huge, and our models need to scale well with that. It's not just that it should work with a small snapshot or small snippet of code, data that we had, but instead it should be scalable. Our model should be useful for larger data sets as they are coming in, right? So that's that. And then there is experimentation. And personally speaking, I feel there should be an entire course on experimentation because this is a huge topic, the design of experiments and how to um, find out how effective models are. But I'm going to introduce you to something that's known as A/B testing, which is pretty common in industry. You might have come across that. And if you've taken any statistics class, you probably already know Z-tests and T-tests. So that's precisely what A/B testing is. But just because like that term is used frequently on like in the industry, and so that's something that you should be familiar with. Okay, so let's begin. Uh, as I said, like why is scalability important and what exactly is it? So it's like the ability of my model to be able to capture larger data set and workload, and that like the more scalable your solution is, the more scalable your model is, it's more reliable because eventually you are implementing like your machine learning model to get some results for a particular business, let's say, right? And so I should be like, if I implement or if I utilize a machine learning model, or if I go and suggest that this is the model that we should be like implementing for this problem, it should be able to handle large amounts of data and then get relevant like outcome. So that's why scalability is so important. And even before we jump into like how to and so there is this article that you must go and read about scalability. And basically we need to understand where exactly and how is the data coming into our system, and then we should know how like what are all the tools that are there in order to deal with these larger data sets. So that's then like I can only give you an overview in a single lecture, but if you are familiar with these tools, you can just like go and do your own research as you've been doing in this course throughout. And I know that you have the ability to just like go and pick that up and get started from there. So that's the whole goal of today's lecture. Okay, so as I said, the way we utilize data in our models and the data sets that we've been using have been built as such or have been like manipulated so that we can just pick them up and implement our model on them, right? They did not originally come in that form. So like what are some of the layers? And by the way, like big data is essentially a term that's used because like we have humongous amounts of data, and like the way we are capturing it is like from multiple sources and putting them all together and then building models on them, right? So there are certain layers. There's this like high-level architecture that works in to get us that nice data set on which we build our models. So it makes like it's useful for us to know how this is coming into getting like to the final form, and then we're using it to build our models, right? So this is a high-level structure of how we capture that data. And obviously, we have multiple data sources these days, right? And we have to, like, in some ways, put all of that together, as this like diagram shows here. And there are three, like, I would say, basic processing stages or pre-processing stages in your, like, the way this data is captured. The first one is data ingestion, and then comes the data storage, and finally the data processing. Once we are done with all of this, and in fact, in today's systems, these are like very well orchestrated as well. So there are like ways of orchestrating that. There are tools for that as well. Then comes like your job as a data scientist or your job as a machine learning practitioner to go and utilize that to train your model and get some results out of that, right? So let's actually dig deeper into what data ingestion is, and then what like data storage and different ways of storing data, and what all are the different tools that are used for data processing. Okay. So by definition, data ingestion is like how you move around your data from these different sources to some storage medium, to some centralized storage medium where it can be accessed, used, and analyzed by the entire business, by an organization, whatever you're building your models for, right? And the destination for these is usually a data warehouse, a database, a document store, and so on. And sources can be many, right? So there can be multiple sources. So think about this as like data coming in from click streams. So click stream is nothing but customers interacting with the website, customers coming onto your website, clicking things. Maybe just like, let's say it's an online retailer's website. So you're just like looking at the items, clicking them. And so all those impressions or all those engagements with the website need to be recorded, because you will eventually need that data to make good recommendations, let's say, right? And that is like recommendations are directly linked to your revenue. So that's important, right? So clickstream data, for example, then live videos, like for example, YouTube, right? So how people are interacting with the videos, whether they are like liking it, disliking it, for how long are they watching it. So all that data needs to like come into some I would say centralized place from where I can pick that up and make some use of it, right? So that entire process is known as data ingestion. So it's like the backbone of any analytics architecture. And like sometimes it also includes like reporting as well, but mostly it is like the first layer in your entire data flow process. The very first layer where we as like, let's say we are customers on a website. So we are like the producers. So we are producing the data, and then it's flowing into some storage where we store it, and there could be like different, and there are like many, I would say, platforms available that make that storage easier. There are different types of databases available, and so on. So that's like an important aspect of like capturing your data. So there are two types of ingestion, like high level, there are two types. Otherwise, there are like many different parts of ingestion as well. So the first one is streaming ingestion. That means you have this continuous data that's coming in. So streaming is like people watching videos on YouTube, or people like going onto a music website and listening to music, and then that's like continuously coming. So there has to be a different way of reading in that data and then storing it somewhere, right? And then utilizing it later on. So that's the first one. So data is sourced, manipulated, and loaded as soon as it's created, right? So that's like one kind of ingestion. And obviously, this is more expensive. This is more difficult. It requires more sophisticated sort of architecture to capture this. And we also need systems that continuously monitor this data source, right? So this is the first type, which is like streaming ingestion. So for example, some of the examples are like clickstream, change data capture. So this is a technical term, change data capture. And this actually is talking about, let's say there is a user ID, and there's a user and they have like an ID, and they come to Netflix often, right? All of us, we go visit Netflix every day, And so we want to capture my Netflix wants to capture the history of my engagement on Netflix, right? So it's not something that just stops like once I go and watch a movie, but it's like an ongoing process. And it's important to capture that because you've seen, like, you've built machine learning models, so you know that like that history of my history on Netflix is important to Netflix, right? So that's what this like measures change data capture. So we have to like capture that change as it's happened, as it's going on, as it's like, because it's an ongoing process, because we might need that data at some point. So again, this is like a continuous monitoring of a user and like long term. So this also falls under the category of streaming. And then live videos, obviously, you know that like it's not just the data of like the video, because video is like a product, right? So the attributes of that, but also users of people who are watching it. So that's a continuous process, right? So there are more sophisticated ways of doing data ingestion when this when streaming ingestion is happening. I think some of the tools that are available for this are like Kafka, if you've heard of that. Kinesis comes with AWS. So those are some of the names. I think as far as I remember, Kafka is from Apache. So those are some of the tools that are available for streaming ingestion. So getting the data and putting it in a storage like a database or something. So those are some of the tools, if at all you are required in future to do some kind of stream ingestion, those are the go-to places. So just like go and explore Kafka or Kinesis. There might be others, but I'm familiar with these two. All right. Then there is batch ingestion, which typically happens in like any like usual website, wherein periodically like people go and buy things, and maybe like you don't need to continuously monitor what's happening on the like. Of course, you're monitoring what's happening on the website, but then you take snapshots of those. Like you take snapshots of what's happening like in a certain like periodic sort of bucket, right? So that's what batch ingestion is, like periodically collect and group source data and then utilize that and send it to some destination system or some storage place, right? So again, we can make or build groups here, groups processed on any logical ordering and like basically schedule something so that like I collect data every 7 days maybe, right? And then process it and take it further down this like this flow, right? So maybe I capture data every 7 days, and then I utilize that from the storage for processing. Otherwise, I don't process it like continuously. So that's another way of doing data ingestion. So high level, there are two ways. Just like I think this is sufficient to remember: streaming ingestion and batch ingestion. Okay. And then I think you're familiar with like databases, so I didn't want to go too much into the details of that. So there are different types of databases now, depending on the type of data we have, and then how can we like distributed file systems for high performance access to data and and scalability as well, right? So I'm not sure if you've come across HDFS or not. Like you must have come across that term at least, right? So what is this Hadoop? Hadoop is an open source distributed processing framework that helps you manage data and store for big data applications. And high level, how this overall architecture works is that you have this like data coming in, which is distributed. So what it does is that there is a name node, and then there are these like data nodes. And this name node maintains, and I think I should show you and this link actually gives you like a good description of what HDFS is, but this is how usually huge chunks of data are handled. So there is a name node, and then there are these data nodes that are connected to this name node, right? So the name node is going to keep track of like so data comes in, and this name node is going to take care of like certain partitions in the data. So I'm not going to save everything at once in one place, but I'm going to partition my data. So the way I partition it is that these different data nodes get different partitions. I don't know which ones. My name node is going to assign those partitions to these data nodes, right? And so what happens is that like I'm able to maintain these different data nodes with different snippets of like from my overall file system, which is huge. And the way I can access these and control these and use these is by this name node, because it's going to keep track of like which snippet or which part of my data or which segment of my data is in like which data node, right? So this is like the controller, the manager, everything of my data, which is like saved in like different data nodes. All right, we'll come to replication in a bit, but there can be some issues like obviously we are getting every file, we are accessing everything through this name node. So sometimes there are two name nodes, like one is the active name node and one is the passive, which is not shown here for some reason. So like a newer sort of architecture is that you can have like two name nodes, and you can keep one of them active, one of them passive, just in case of like failure of one of them, you still have like a backup type somewhere. And so that's like replicated in that active passive, and you kind of switch between the two depending on like your application. Okay. So yeah, it makes sense to go into this one because you will definitely come across this HDFS architecture when like going out and working for some like real world application. You might come across how this HDFS works. To like remember, one thing is that HDFS data is written on the server once, and it's used like reused multiple times. So if you so here they're showing something called replication, and that's what it means, right? So basically, you don't want to. So this is something sometimes known as exactly one semantics, if you come across that term as well. So that's what this means, like data written on the server once and read and reused multiple times, numerous times, right? And of course, name node keeps track of where the file data is kept in that cluster, and then it can like have multiple data nodes and then access them, but it reduces the time and like helps in scalability overall. So that's the general architecture. Of course, if you're interested in that, definitely go into the details, like reading this link would help. Yeah. Yeah. So why this is like replicated is because this enables parallel processing. So you're not processing everything all together. So that's like making your overall processing faster and your storage faster as well, I would say. Okay. So this was the second block in our overall like getting data, doing something with the data ingestion part, and then storing it in HDFS and other formats. So HDFS is just one of them. There are other tools as well that are used. As I said, I'm pointing you to a few of them, not all of them, because like obviously it's like almost impossible, but there are other tools as well for data storage, for big data storage. And then finally comes the part of data processing, after which we get the format of the data that we've been using in our projects, right? So the final part is data processing after data ingestion and storing. We need some kind of a processor to extract features and labels from the data, and the way we've been using our data sets, right? So Apache Spark is one such tool. It's an open source, general purpose distributed computing engine for processing and analyzing a large amount of data. And it's similar to Hadoop MapReduce, which is another tool, right? And it works within the system of distributed data, just like we saw just now, around like different clusters, processing the data in parallel. And then you can utilize this to get your final data set the way you would like to use it. And I just wanted to add one thing, that there are other tools available now. For example, Apache Airflow, which is again an open source tool that can using which we can actually automate this entire workflow. So Apache Airflow is something to definitely go and explore, and it is like a very robust platform for data engineers, because you can like orchestrate this like entire workflow of getting data and then storing it, and then the distributed or parallel processing, and then finally getting the data in the form that we have. Okay, so I know this was a short introduction to this entire process of how do we get data and how does it like come into this form in a real world environment. And then once we have that data, now we are ready to deploy our models with that. Okay, so having discussed this, the other part that I wanted to talk about in today's lecture, as I said earlier, is experimentation. And experimentation is important because, like, so what happens is that I did all this. Let's say I'm done with data ingestion, data source, data processing, and I built a model, right? So let's say I built some model and I implemented it, and that's it, right? So let's say I built a recommender system model, and I included more personalization in that model, and I have to deploy it, right? But I don't know the real world impact, the business impact of that model on on my real customers. So what should I do? Before I do that, I need to do something that's known as experimentation. And there are many different tools and different ways of doing experimentation. One of them is known as A/B testing. So I really want to like test my model before, like I would just test it before I actually deploy it everywhere, so that I know that this model does bring about a change or not, right? So let me go here, right? So there are different ways of experimentation. We even use multi-arm bandit approach sometimes to do that, but I'm just focusing on A/B testing part, and specifically I'm focusing on the statistical testing, which is ZTest and TTest. And you might come across this a lot, right? This even like for interviews and all, this question is asked a lot, like what is A/B testing? And most of these platforms, including Facebook, I think, they use A/B testing for like their ads, and if there's a new feature added, and so on. Okay, so what is A/B testing? Well, A/B testing is a randomized experimentation process where you will have two versions of some variable, right? Or maybe like two versions of a web page or some new feature, some added new feature that is shown to different segments of the website. So basically you have two things, like two groups of people, and let's assume like Facebook added a button somewhere, right? And they wanted to check like how would like people respond to that. And so what they'll do is there is an existing version of Facebook, and then there is this like new feature. So the existing version would be termed as the control group, meaning we are just using it as it is, right? And then there is going to be this treatment group, because we are going to offer this new feature to that treatment group. So we are treating them with something new. So it's like, and actually the origin of the term comes from medicine, where you had like two groups and you're testing the effect of a new drug, right? And what I want to find is whether this new feature impacts the customers or not. And so if there is a greater like some kind of a positive response from these new like the treatment group, then I could say that yeah, this is a good feature that I should add, right? Or for example, on platforms where you have like ads, right? So let's say I'm giving some kind of a discount or a coupon or something, right? So I want to know if I give this discount, whether more people will click on this ad or not. So in order to find out whether that happens or not, I will show the same ad as it is, right, to some customers, but I'll show this like coupon and this discount to some customers and see if the click rate is increasing or not. So those kind of examples, right? So the like a few definitions here before we actually jump into the details of like how this testing happens. So the first one is baseline. So for example, think of this advertisement campaign where they're like giving out coupons and discounts versus like no discounts and no coupons, and they're trying to see if that helps in people clicking their ad or not, right? So the baseline conversion rate will be the current rate at which like the users click something. Or here, I think I took an example where I wanted to see if new users sign up for some premium account or not, right? So the same thing, like I'm really trying to find out if my premium account offer is going to be accepted by more users or not, right? So the baseline conversion rate will be the rate at which like the new users like sign under the existing design, right? And then there is this control group and test group. So we'll have like two groups of users. So the question arises like, how do we come up with a control group and a treatment group or a test group? Sometimes it's also known as a test group, right? So users will be randomly selected. So random selection is important because as in statistics, we don't want to do any kind of bias in our models. And so we'll randomly select both the groups. That's it, right? The sample size, meaning how many customers should be there in each group. Roughly speaking, there should be equal number. So when you're picking your control group and you're comparing with your test, obviously test group would be some people whom you decided that you're going to show this ad to with the discount, right? So the idea is that when you actually go and do the testing, it's a good practice to have like both of them as like equal numbers. Okay. And then the sample size that you decide on will determine how long you'll have to wait until you, like in a real world platform, you'll have to wait for some time until you actually collect that much data. Okay. So this like A/B testing can be done in many different ways. And believe it or not, you can even use regression for this. I have used it in some of the experiments because it's a more robust way. The only thing is that you should be clear enough on like what is your dependent variable and what is your independent variable. That's like, but let's not talk about regression right now. Let's talk about two statistical tests, the Z-test and the T-test. So before we do that, we define two hypotheses. The first one is the null hypothesis. So basically, you're saying that this new feature that I'm adding or the discount that I'm offering to customers is going to make some change. That's what you're anticipating. That's what you want, right? So your hypothesis is that this is going to make some change, right? This is going to make the users click more. Now, your null hypothesis is that there will be no change, right? So that's the position that the design or like the offer is not going to make any change. So that's what it suggests. So null hypothesis often denoted by H sub 0. Sometimes if you see in like textbooks and other places, H sub 0 is the null hypothesis. The alternate hypothesis is the opposing position, meaning that yes, it is going to bring about a change. So like one way of like thinking about the null hypothesis is that when we do the tests and then when we evaluate the results, what we like should think about is that if there was a change, we are really trying to find out whether the change was only due to randomization, because you have two different groups and most likely the results will be slightly different. Let's say I picked 500 people who were shown the discount, 500 people who were not, right? And then I captured their click rate, how many times they clicked. There would definitely be a difference, right? It's no way possible that both will be the same. So my goal is not to see that the number was different and so yeah, this is converting more than this. My goal is to see whether it is statistically significant or not. And by statistical significance, I mean that whether this difference in the control and the test group was caused by randomization alone, or was there some other effect? So statistically speaking, that's what we are trying to find out. And so that's why we have to do some statistics and some analysis before we establish that, yes, this difference is statistically significant. Okay. So of course, like there are more details about A/B testing here. I think one of them is an article from Harvard Business Review, which is a very good one. Please go and read that if at all, right? So let's actually try to understand what to do when we are asked to do some kind of A/B testing. And now you understand why you need to do A/B testing, because before actually deploying your new model, you need to find out whether it's useful or not, right? So we can like compare these two groups, the test and the control, in multiple ways. My recommendation usually is start by plotting, start by seeing and like um, the probabilities of getting like the results from both of the groups, because like visualization goes a long way. But that's not the only thing that you can do. So you can do two things. There is a Z-test and a T-test. So as the name suggests, the Z-test computes a test statistic, and then it compares it against some significance level and some probability that we decide, right? So what are these tests and what exactly are they trying to find out, right? So there is this like Z-test, which is used when you have a huge sample size, typically more than 50. So if you have more than 50 and your population variance is known. Okay. So in like experiments like these online, most likely my population is like, let's say on Facebook, my population is like, I don't know, whatever billions of people on Facebook. And it's like difficult to get that. So there are ways. So for example, if you have come across central limit theorem, you know that we can make some assumptions about like large data sets and say that like this is almost normally distributed and come up with the parameter, estimate those parameters. And so we can say that the population standard deviation is, or population variance, which is one and the same thing, can be estimated because the sample size is huge. So the good thing is we usually have, like in big data sets, we have a lot of data. So we can make those assumptions. So either one of them is okay. Like usually we used to have this issue of like which test to use between Z-test and T-test when we were doing some kind of a clinical trial, for example, and you have like very few people for that, right? So then it was crucial which test to use. So that's why I just like mentioned this here. If the sample size was really small, then the assumption is that it follows a T distribution. Then again, if you remember from your statistics classes, there isn't a lot of difference between T and Z, like the normal distribution, except that it's like a scaled version of the Z or the normal distribution. And so the sample size is small, go ahead with the T-test, and you know the population variance. But now, as I said, with big data sets, you can use either one of them because you can do some extra analysis to um, to fulfill the assumptions of both the tests. Okay. So we can do two analyses. The first one is analysis one, assuming the control group represents the population, because it's like, let's say my control group was size 1000. So it's like way above 50. So even according to the principles of statistics, I can safely say that it represents the population. And so I can calculate its mean and the standard deviation. So normal distribution is a parametric distribution. So I know what needs to be done. So then I can compute the Z statistics, check if it lies in the rejection region. Rejection region is nothing but the tails of my normal distribution based on my significance level alpha that I decide, right? And usually in these experiments with big data sets, we use a 0.05 alpha. Okay? So I have like an overview of this Z-test, just in case you don't remember from the statistics class. So a Z-test is a statistical test that is largely used to determine whether two population means are different or not. In other words, like I have the test group and the control group, and I'm trying to find out if the difference in the mean of the two groups is statistically significant or not. Okay. So how do we run this test? Well, the first thing that I'm going to do is state the null hypotheses and the alternate hypotheses, right? So the null hypothesis is going to be, well, there is no difference in like my control and test, right? And then I choose a significance level. So as I said, the alpha level or the significance level is the probability of making the wrong decision when my null hypothesis was true, right? So we decide that it's more like because you know the idea behind confidence interval. So like with 95% confidence level, right? I can say if I chose a significance level of like 0.05, that means with 95% confidence, I can say the other way. So usually we use 0.05 as alpha, but sometimes we can also use 0.01 or 0.1 depending on our application. And then, okay, so this used to be like when we were calculating Z by hand, right? So I know because I used to teach one statistics class where I made students do this by hand, but now you don't have to do that. Like there are softwares available. There is this single line of, I think, stats model. I don't remember which one is there in Python. I think it's stats model, scipy.stats model. It does that in a single line anyways. So find the critical value of Z in the Z table, and then you will have the Z statistic calculated using the data, right? So you have the Z statistic, which is nothing but a value that you calculate using your data. And then you compare it with the value that you got from the table. So usually for an alpha of 0.05, if you remember, this is like 1.96 or something. If you're doing a one-tailed, if you're doing a two-tail, it's 1.64. That's what I remember roughly. So just compare that Z value, whether it is more than that critical value or not, or is it less? So if it's less, it lies in the acceptance region. If it's not, then it lies at the tails. That means it's the rejection region. So yeah, so depending on that, you support or reject your null hypothesis. Okay. All right, so here I have like more details about this entire process. So the example that we were looking at was this. I think I mentioned that somewhere. Yeah, so for example, let's say we are doing an A/B test for a hypothetical company that's trying to increase the amount of users that sign up for a premium account, right? So the way I like to go about it is that I will do both my Z-test and my T-test, and then eventually come up with like my final recommendations. Okay. So here is like the overall process. As I said, according to the central limit theorem, I can calculate the sample mean, and that can be used to approximate the true mean because my sample size is huge, so I can do that. And then this can also be used to compute the standard deviation. And like for this example, maybe we are okay if we are just like calculating the conversion probability, meaning how many people clicked versus the total number, right? So that can be considered as the probability. And my null hypothesis would be that the difference, this D, equals the test conversion. So TCR is the test conversion, and CCR is the control conversion, is equal to 0, right? So because my null hypothesis is saying they're not like different. So basically that zeros should lie within the confidence interval, in other words, right? So I would like to check if D is greater than 0 or not, because if it is, then I can reject the null hypothesis, right? So obviously we know how to do like a Z-test with 95% probability. So I'll go and calculate the standard error of the data. Standard error is like another word for standard deviation, except that we are taking the sample size into consideration. And then using that, I can compute the Z value and then see whether like my D, like this thing, lies within that like rejection region or not, right? Okay, so this is like the Z-test, right? And then what happens with the T-test? Well, there are a few assumptions that are there with both the Z and the T-test. As I said, with the Z-test, we can fulfill the assumption because if my data set is huge, it can be considered to be normally distributed, right? So in this one, we can use T-test for independent samples. And there are two, you will come across these two terms. So there is a paired T-test and this like independent T-test. Paired T-test is usually for situations where you are trying to find out if the same user like shows some changes in their behavior if this like particular new feature was offered to them, right? So then we do a paired T-test. In this case, I'm not bothered whether the same user is exhibiting any kind of change. I'm just like in general bothered about this new feature, right? So there's a difference there. And so I'm using like this T-test for independent samples, meaning they're not like we are not pairing them in any way, so they're not related to one another and so on, right? So if you're doing this independent T-test, then there are like certain assumptions that need to be met. And this goes for all statistical tests. Please go and check, because I know that there are other tests as well. So you should go and check the assumptions first, because if those assumptions are not met, or you're not able to somehow justify that those assumptions exist, then like the validity of your tests doesn't hold, right? So the assumptions are there should be one independent categorical variable with two levels. So in our case, it is met because I have like a test and a control group. So two levels, right? Just imagine the data set, right? I'll have two levels, and then people, yes, they clicked, they did not click, click, did not click, and so on, right? So it matches. And then one dependent categorical variable. So that's okay. Okay, so independence of observations mean each subject should belong to only one group, which is also okay in this kind of a scenario for A/B testing. So that's fine. And then the dependent variable must follow a normal distribution. We can go to the central limit theorem and say yes, it does. Here, this is important, and many people just like bypass this, the homogeneity of variance for both of them. So there is something that's known as a Levines test. I don't know if you've heard about that or not. Whenever you're doing a t-test, you should always do that. Maybe I forgot to mention it here. Now that I'm seeing homogeneity of variance, I remember. You should always do that to see if there is a homogeneity of variance. But so what that test is going to do is it's going to tell you whether the variances of both the groups are like in some ways comparable or not, right? So that's an important assumption. Always do a Levines test along with the t-test. Okay, regardless, the rest of the process stays the same. What you do is state the null hypotheses, state the alternate hypotheses, and then just go ahead and do the entire calculate the t-statistics, see whether it lies in the rejection. The rest of the stuff stays the same, except that we are using we are assuming that it's a t distribution instead of a z, which is pretty much like similar to like a normal distribution, right? And instead of a z statistic, you're calculating a t statistic, right? Rest like significance level, alpha, and everything stays the same. You still need to find out whether the t statistic lies in the rejection region or not. Another important point I wanted to make is that sometimes, like in some of the experiments, you're comparing the difference in the means of the two populations. So the mu is the thing that you're computing. Sometimes you're calculating the difference in the proportions, right? So there is a slight difference in the formula of like the z statistic and the t statistic when we are calculating the proportions versus mean. So check that before. And I think most of the packages in Python, they handle that anyways. So that's not something to worry about, but just like remember that the way we compute z and t may differ. All right, so that's that. And we can do, as I said, like another thing that you can do is you can do a regression analysis as well, where like your your dependent variable could be the rate, the conversion rate. And then like the good thing about regression is that you can also use other attributes of users, like their age, their location, and so on. So that would be a more robust kind of an analysis, right? And you can still get a p-value there, like, and check, have a significance level and see what's going on. Okay. I'm assuming most of you are already familiar with these tests, but I still wanted to go over this. And then comes like the final part. This is more like a post hoc analysis where you should, after doing any statistical test, do a power test. And basically this, like we did some tests and we found out like that the effect was significant. So we rejected the null hypotheses and we said that yes, the effect is significant, right? If we reject the null hypotheses, that's what it means, right? Now, the power or the statistical power of a hypothesis test is the probability of detecting that effect if there is a true effect present to detect. Okay, so very like confusing language, I know, but basically we are really trying to find out that was it a result of only my experiment? Maybe I set up the experiment in a certain way that I rejected the null hypothesis, or actually we needed to reject. And one thing to remember is this power analysis is valid only when I rejected the null hypothesis. Otherwise, it's not applicable because that's what we're trying to see, that, okay, we found an effect. But because if we did not find an effect, then power analysis is not something that's so much important then. But here we are trying to find out, okay, we found an effect. Is it really there? Right? So, and with what confidence can we say that it is there? That's kind of a like another interpretation of this, right? Okay, so the way we do that, and even before we actually jump into this, like when we rejected or when we accepted the null, basically we say rejected or not rejected, right? So when we rejected the null hypothesis, we were looking at like a p-value, right? And this like p-value was the probability of observing the result given that my null hypothesis is true. But still I observed something, right? So that's the p-value, and that p-value has to be less than my alpha. Remember the significance value, 0.05. So if my p-value is less than that, then only I can reject my null hypothesis. Otherwise, I cannot. Right? So Having said that, I know that's like a lot of information, but if you just go and read the Z-test, you will that will be clear. But regardless, like if we say that P is less than my significance level, right? So basically, I'm saying that I don't know how to say this, like the probability of observing this result, given that the null hypothesis is true, was very low. So that's why I can reject my null hypothesis, because that like this result couldn't have been only because of randomization alone. There is something else that's present, right? So we reject it, and like if this P is greater than alpha, then we fail to reject this, right? So there are two types of mistakes that can happen when we are doing this kind of analysis, right? So the two types of errors that can happen in our hypothesis testing, and that's why we are like looking at it, is like the type 1 error, which is a false positive, or a type 2 error, which is a false negative. Now, my power analysis usually helps when I get a false negative. Okay. So what it does is that this like statistical power, or the power of a hypothesis test, is the probability that the test correctly rejects the null hypothesis. And we want this to be high, right? We want the power of my test to be high, because with high probability, I'm saying that I rejected the null hypothesis, right? So this is like saying that the probability of a true positive result, it is like only useful when the null hypothesis was rejected. Okay. And like, as you can tell, higher this probability, meaning higher the power of my test, the better my test was. So we should be able to establish that with this power, usually 80% or above, I can say that I rejected the null hypothesis, right? So again, basically we're saying that we have a lower probability of making a type 2 error. So the way we define mathematically the power of any test is like 1 minus the probability of getting a type 2 error. So that's the formula for that. And higher the probability of detecting an effect when there is an effect. Again, like same thing repeated, but with different words, right? I detected an effect because it was there. And so that's why I rejected the null hypothesis. And so the power of my test is high. And as I said, if you fail to reject the null hypothesis, then this power doesn't make any, it's not significant. You don't like, it doesn't mean anything because I already failed to reject the null hypothesis, right? So that means there is no effect. So how can I find the significance of that effect? So there is no power then, if that makes sense. Okay. So again, like as I said, you can mathematically write 1 minus the probability of getting a type 2 error as the power of a test. But there are like more, like there are other analyses that are available that you should usually go on and do. And these are known as like post hoc analysis. And like some of them are like finding the effect size, sample size, significance, like all these 4 actually go together. So the effect size, like how high its effect is, if you rejected the null hypothesis, what should be the sample size? So the power of a test is something that can be like flipped over. Let's say my desired power of a given test is 80%, right? And so there is a relationship between sample size, significance, that's alpha, and effect size and statistical power. And using these 4 variables, you can actually determine the sample size that should be there to achieve a certain statistical power. Now, there is like another, I would say, flip side to this, because like a larger sample usually will make an effect easier to detect. And so we'll have a higher power in that sense. And we can like increase statistical power by using like larger data sets, which we usually have in like today's world. Okay. And yeah, so power analysis, basically like this term here, power analysis means that we are estimating one of these 4 parameters given the other 3. So we can actually design experiments. So there is this whole field of design of experiments where you can keep one of them like fixed, okay, and then you vary the other 3. And then again, one of them fixed, vary the other 3, and like design an experiment to see the impact of each of these factors on the power of your test, right? Or on the sample size. And so you can determine that this is the range of the sample size for this experiment that would result in a higher power test, given this like significance and given this like effect size. So like, again, as I said, these four can be used to design experiments and build like some good, I don't know, tests that can help us determine good sample size for any test. All right. So I think that's all I wanted to discuss today. There is this extra resource, and this one actually is a link to some like quick review of the statistical concepts that you might require in building your machine learning models. And like, please go over them if you need to brush up, like, because statistics is, I would say, an important part of any like machine learning model, any machine learning project. And not just that, like, not just from the perspective of like building your model. As you can see here, before we deploy our model, we need to go and check the effectiveness of our model. And that can be done through like statistical testing, through A/B testing. And in addition to this, I would like quickly mention nowadays with like more data that we have, there is another like multi-armed bandit approach that we covered in reinforcement learning that's also used for this experimentation. So high level, the idea is that let's say I run my experiment on some online website, right? And I noticed that my control group was showing like the base conversion rate, like this thing that we, I think, uh, defined here. So where is it? Yeah. So the baseline conversion for my control group, let's say, was around 7%. And like the first 3 or 4 days of my experiment running on some platform, I noticed that my test group is just 4%, right? We talked about bias last time, if you remember. So maybe I designed my experiment for 2 weeks, but I just noticed that there is like this low conversion rate for the test group. So I just conclude that this like new feature or whatever it is not good. And I just like stop my experiment. But that's not a good approach because that might include bias, and you do not really know that like later on, maybe in the next part of the week, that test group would have picked up, right? And so what we do here is that there is this like, if you remember from reinforcement learning, this epsilon greedy approach is used, and that's like again multi-armed bandit type approach, wherein what you do is you keep like reassigning people and like to different groups. You keep reassigning from test to control group, and then follow this like with some epsilon probability from one group to another. And so what will happen is it will, although it will keep these things randomized, but you will be able to strike a balance between exploitation and exploration, right? Because like, let's say I wanted to exploit my control group completely, right? But then I also want to explore what's happening in the test group, but I'm like stopping my experiment a little earlier than I wanted to. So this multi-armed bandit approach with this epsilon greedy algorithm is a newer like version of experimentation, which obviously I didn't mention here because like, yeah, it's definitely catching up, and maybe I can point you to a link or something. But that's also something that we can do. So you don't have to just like stop at a statistical test, but do this kind of like reevaluation and reassignment of people from one group into another, and notice like what happens when you strike a balance between exploitation and exploration, right? So reinforcement learning type approaches have also been like are the latest trend when it comes to experimentation. So that's something that you should definitely look into. Uh, yeah, other than that, I'm not remembering any specific thing. Yeah, I pointed you to this link because I wanted you to go over like these topics, not necessarily this tutorial as such, but these are some of the important topics that you should be familiar with when it comes to experimentation and working with data. So of course, like these different types of distributions, what is correlation, statistical hypothesis testing. We did cover like ZTest and TTest, but there are others as well. Because like what happens when there are only categorical variables? So what kind of tests should we use and so on? Estimation statistics. I'm assuming like you're already familiar with most of them. Just like going over like quickly those topics would help. So that's why I just pointed that link up there. Okay. Any questions before we end? I think I gave you like too much information anyways. So like I usually make all of you like brain dead for some time. So then like, yeah, you can go back and like look through the links it's not that hard. Like the statistical analysis is, I think, the fun part. So it shouldn't be like overwhelming. All right, so that's all I have for today. And I will like just let me like reiterate what I said last time. So I will be there on Tuesday in my WebEx room. So you can come in if you want to discuss your projects or any other thing. We can do that. But there is not going to there is no lecture that day. And so just like giving out a secret, I just had 25 lectures. So like I'm short of one. Yeah. So that's why I thought, okay, let's not do it.